In this screencast, we're going to look at how to debug the shell lab. Along the way, we're going to look at some advanced features of GDB that we didn't cover in the last screencast. Some of these features are actually new to version 7, which was recently installed on Ada. Towards the end of the screencast, we'll also look at a subtle issue with a naive implementation of the child process handling logic in the SIG-child handler. Okay, let's get started. So the first thing I've already done is I've made some changes to the tiny shell implementation, and I'll go over those quickly. I did that so that we'd have something more to talk about. So in the eval function, some of this stuff should already be familiar. First, we declare the argument vector array that we pass to parseline. We get back the result of parseline, which tells us whether or not we want a background command. And after getting the argv, the parsed argv back, this is new here, we're checking to see whether or not it's an empty line, and if so, we simply return from eval. If it's not, we go on to the if statement we saw before, where we fork a child, we exec the process or the program, and we print command not found if the program isn't found by exec, and exec returns an error, in which case we exit. If not, of course, that program takes over the child process, and the child process doesn't see the rest of the code. In the parent process, I've added a bit of code here, a one-liner, that adds the process as a job to our job structure. And notice that this method I didn't need to write. The function is pre-implemented. And I'm not going to go over add job, but that's something you should do. This conditional here makes use of the bg return value of parseline. And if you're not familiar with it, the idea is if bg is true, that is it's 1, then I populate the job structure with the bg constant, which is also predefined towards the top of this file. Otherwise, I create it as a foreground job. After adding the job to my job array, I go on to check to see if in fact I created a background job, and if so, instead of calling wait directly, I'm going to call waitfg. This is yet another change that I've made. So waitfg is a function meant to be called, again clearly from its name, to wait for a foreground process to complete. Notice I'm passing it the PID of the process I just created. Let's take a quick look at waitfg. Waitfg is right down here, and it's a short function, at least in its current incarnation. And what it does is it checks in a tight loop where it sleeps 1 second at a time. It checks to see if the foreground PID in my jobs array is still equal to the PID that I sent in. The fgpid function is also pre-implemented, and that takes the jobs array as an argument and returns the value, the PID of the foreground process. So where does the reaping actually occur then? Because notice there's no wait in waitfg. Well, it turns out that I moved that as well down to the SIG-child handler. And the SIG-child handler, we all know that gets called when the SIG-child signal gets sent to the shell. The SIG-child handler waits for a child, and notice the comment here, this is pretty important. This isn't the ideal way of doing it for more reasons than one, and I'll talk about one of the reasons later. But we reap the child, and we delete the job from the jobs array. Delete job, of course, is also pre-implemented. And those are most of the changes. Before debugging my shell, of course, I'm going to want to make sure that I make all the necessary binaries. And I've gone ahead and done that. And at this point, I can just do gdb./tsh to start debugging my shell. Now at this point, if I wanted to, I could go ahead and just use my shell as I normally would if I invoked it from the command line. And this isn't a bad idea, because if something goes wrong, you're already within GDB. So to do that, we just type run without having set any breakpoints. And it says it's starting my program. So I could go ahead and start typing commands, just as I would if I invoked TSH from the command line. So I type in binls and notice that it produces the output, after which it gives me my shell prompt back, demonstrating at least partially that foreground processes work. Let me check to see if binls was properly reaped. So I'll execute binps, which remember shows me the processes that are currently running. And one interesting thing to notice is that in addition to TSH and PS, notice that ls was in fact reaped. GDB is also running as a process. Of course, GDB is currently debugging TSH, and so it shows up with a lower PID. It was started up earlier than we actually ran TSH. Of course, I can also quit my shell and that drops me back to the GDB prompt. Previously, when we debugged a program, we would always set a breakpoint at main so that when we started running the program, we would stop execution at main and we could start debugging. This time around, it's really not useful because we don't do anything in main. We just read stuff, all the action happens in eval. So while I could set a breakpoint at eval right now, I'm not going to do it because I want to show you another trick. So let me go ahead and start running the program, typing run, and that takes me to the TSH shell. So if I were to type a program, the name of a program like binls, I know that takes me right back to the shell, so that does me no good because there's no breakpoint at eval currently. Now if I'm doing this, I realize that there's got to be a way to get back to the GDB prompt. And in fact there is. It's a very easy way, and that's just hitting Control-C. Now you'd think that by hitting Control-C what I'm actually doing is sending a sigint signal to the tiny shell. Unfortunately, that's not what's going on. This time around when I send a sigint signal by hitting Control-C, that sigint is actually getting intercepted by GDB, which is debugging the tiny shell, and GDB drops me to the debugger prompt. Now you'll have to take my word for it, but I can try and prove this to you. So if we take a look at the sigint handler function as defined by the tiny shell, you'll see that I made one small modification. And that is that when the tiny shell receives a sigint signal, it prints sigint received. I never saw that output anywhere here after hitting Control-C, and it would have come right here. So in point of fact, the tiny shell never received sigint. GDB received sigint. So that's all very well and good because it gives us a way to get back to the GDB prompt. But it does beg the question, how do we send the sigint signal to the tiny shell? Well, it turns out there's a GDB command to do that. And the command is signal followed by the name of whatever signal we want to have delivered. So this time I want to send the sigint signal. Once I hit enter, GDB is going to send the signal to the tiny shell and continue execution. So let's try that. So notice what happened. First of all, GDB told me I'm continuing with signal sigint, and it delivered the sigint signal to the process, that is the tiny shell, and the tiny shell received the sigint, which got delivered to the sigint handler function, which in turn printed out sigint received right here at this line. And so we see it here, sigint received. Pretty nifty. Let me hit Control-C again. Remember, Control-C does not in fact send sigint to the tiny shell, it just drops me back to the debugger prompt. Okay, now we're ready to set a breakpoint at eval. After doing this, if I hit continue, I get back to my shell prompt. I don't see it because it's already been printed out, but I can type in a command like binls. This time, instead of the process getting forked and exec immediately, I get dropped into the eval function. A couple of things I can do here. Now, because this line of code hasn't yet been run, remember that's always the case, I'll see the line before it's run. I can inspect the arguments to eval, which are printed out here, but just for my own reference, I want to confirm that I can print them out using the print command with command line. And notice it shows me both the address of the command line pointer and the contents, which are of course a string, binls new line. Okay, so let's step over the parse line call, and at this point argv should be populated, so I can print out argv sub 0 and see what that contains. Nice. It parsed the first argument out for me. And let me hit continue, and I know that takes me back to my tiny shell prompt. So I can enter, say binls this time with a flag, -l. The command line is binls-l, you can see that here. And if I step over the parse line, I can now inspect argv sub 0. I can also inspect argv sub 1, and we see that parse line does its parsing properly. And that's the output. While it's certainly useful to be able to set a breakpoint at eval and start stepping through our program from there, one thing to realize about the tiny shell is that all the execution isn't necessarily synchronous, which means that some of the really important stuff that's happening, in our case, where we reap the child process when it's completed, that doesn't happen synchronously. There's no way to step into the sig child handler. What's neat though is we can set a breakpoint at sigchild, or the handler for sigchild. Now let's see what happens now. So if I hit continue, at this point I'm at the shell prompt. I can type bin ls again. And notice I'm currently in eval. So let me go ahead and just confirm once again, just to practice, the value of the path that's going to be given to exec. I can step once more. I notice that's going to step me across that line because it's in fact not a built-in command. And I see we're about to go into fork. So let's go ahead and just let this loose and see what happens. So I'll hit continue. And notice that I get the output for the forked process that ultimately execs bin ls. And I get the output here, and then it hits a breakpoint. Now the breakpoint that I hit this time around is a sigchild handler. And this is really quite cool because now all of a sudden this got called asynchronously by the operating system, of course, to notify me that one of my children terminated or its status changed. So what's interesting at this point is to examine the backtrace. And the backtrace is really quite telling. We see that main called eval, which called waitfg, and we looked at that implementation earlier, and waitfg called sleep, and sleep ultimately called some sort of internal implementation for nanosleep no cancel. We don't really know what that is, but we understand that it's invoked by sleep. On top of that, the signal handler was called. Remember that the kernel does the job of invoking the signal handler. And currently we're sitting inside the sigchild handler. Really quite interesting. We can also use frame to check out our current frame, which is frame 0. Okay, the innermost frame. And we see that we're currently at line 294. This comment you can ignore for now, but we'll come back and talk about that a little bit later. So let's go ahead and step over this first line. Notice that we're calling wait. Now observe that the output before indicates that ls has already run, and our best guess would be that the process that exec bin ls also terminated, and so it's ready to be reaped. So if we step over this wait line, we should be able to inspect PID, which is currently 14811, which means that we in fact reaped a process whose PID was 14811, and we imagine that that was the foreground process's PID. Now we can confirm that actually, because it turns out there's a function that returns the foreground process's PID, which I can call using the gdb call command. So calling fgpid, passing it the jobs array, gets me back the PID of the foreground job, and in fact they correspond, which means that I just waited for and reaped that foreground job. So this next line of code, which I'm about to execute, delete jobs PID, removes that job from the job array. So if I step over that line, I'm now at the end of my sigchild handler. I should be able to call fgpid again, and it'll tell me that the value of that is 0, which indicates there is no current foreground process ID. Now I can also examine the jobs array directly. And notice that currently there's nothing in the first entry of the job array, which would be used if in fact the foreground process ID was still valid. Let's go ahead and hit C again, continue execution, and get back to our shell prompt. So now we've looked at the before and the after of creating a child process. We looked at dropping into eval before the child process was created, and we also looked at continuing from there and seeing that the child process ran to completion, and it dropped us into the sigchild handler, which subsequently reaped that child. So the before and the after of the child process. Now, while this is useful, it would also be nice if we could actually look at what the child process itself were doing. In GDB 7, which is the latest version of GDB installed on Ada, we can do this. The first step to doing this is setting detach on fork to be off. And what this tells GDB is that we want GDB to take control of the process, the child process, after it's created via a fork, and not let it detach from GDB. In other words, not let it run independently. So after doing this, I'm going to go ahead and just type run to start the program from the beginning again. This isn't always necessary, but a good idea sometimes when you want to make sure that the state of the program is not corrupt. So let's just go ahead and hit yes. and I get dropped back to my TSH shell. So I'll type in binls as I did before, and I'm dropped to eval, just as before. And before, when I hit continue, which I'm going to do in a moment, remember that what happened was I forked off a child process, which itself exec binls, produced the output, and I got dropped back into the sig child handler. Let's see what happens this time. Okay, so I hit continue, it says continuing, and it tells me, hey, a new process got created with PID 14977. Now this in and of itself is interesting because I didn't get this notification before, but what's even more interesting and kind of perplexing is that in the shell I'm not getting any output. It's not hitting a breakpoint, it's not getting to the sig child handler. And the reason for that is because it turns out that GDB has taken control of the child process, and the child process is currently suspended. Let's see what's going on in the shell. So I'm going to hit Control C, and let me do a BT for backtrace and see where I am. And this is very telling. So it shows that main called eval. Remember that eval is where the fork occurred. And after eval forked off the child process, it called waitfg, and waitfg called sleep. We're now waiting for the foreground process with PID 14977, which you see matches up with this report earlier. We're waiting for that child process to terminate. Because the child process is currently suspended, of course, it hasn't terminated yet, and we're still waiting for that foreground process to terminate. Okay, so to allow that child process to terminate, one way of doing it is to take control of the child. But how do we do that? Well, if I type info inferiors, and in GDB all processes that the current debugging session are controlling are known as inferior processes. If I type info inferiors, I'll see a list of processes that are currently being controlled by GDB. 14973 is the shell itself, and 14977 is the child process of the shell. So to switch to that inferior, I just type inferior followed by the number of the inferior, which is this number right here, and hit enter. And notice it says switching to thread 2 process 14977, and it's currently in fork. Now I'm not really interested in fork itself, so I'm going to type finish to allow fork to run to completion. And it says run till exit. And now notice it tells me that I'm in eval. The child process is currently in eval. And that makes perfect sense because I just forked. I'm returning inside eval within the child process. If I hit next, I'm now inside this if clause because the child process, of course, returned 0 from fork. I can check that out by looking at the value of PID. It's currently 0. And I'm just about to do the exec. That's really quite cool. I'm now in the other process. I'm now in the child process. Now it's really important actually right now to not allow the debugger to try and step into the exec, or not to try and debug the program after the exec, because that's really going to screw up GDB. In fact, it's going to realize it has no debugging information for binls, and it's going to print out an error. So I really want to allow the child process to go ahead and just run now. Before doing that, it's useful to use the info proc command to examine some information about this process, and I can use that to tell me the process ID, among other things. Okay, so I'm ready to let this process run to completion, and I can just detach from this inferior, and I can say detach inferior followed by the inferior number, which is the number 3 that I used before. So I'll type that, and it says detaching from this program, and I see the output from the program spit to the screen. Notice it happens after my GDB prompt, but of course that's not an issue because this is just a standard output. Okay, so now what? Well, if I look at info inferiors again, I'll see there's only one process, and that is the parent process, the original shell process, and I can switch to that now. So inferior 2, switch to the parent process, and it says it doesn't really know where it is. And the reason for that is because, well, we left it off sort of hanging and sleeping. So I'm going to type finish just to let it finish up whatever it's doing in the current function, and it runs till exit. And notice all of a sudden it drops me into the sig child handler. And this is kind of interesting. What that means is the child process terminated, and now the shell gets a sigchild notification, sig17, and we're in now sigchild handler, which we've seen already before. And I can go ahead and allow this to finish up. That is, return from the signal handler. I can go ahead, hit C to continue, and boom, I'm back in my shell prompt. So being able to debug child processes is a really nice feature of the latest version of GDB. The next thing I'd like to show you is another way of catching those special events such as forks and execs that happen in our shell process. Now to do this, first I'd like to delete all the breakpoints that we currently have set. So doing info break shows me all the breakpoints I currently have, and I can go ahead and delete them by number. Oops. And notice no more breakpoints or watch points. Next, I'd also like to make sure, once again, that I am in fact detaching on fork because I want my child processes to run independently now. I'm going to set that to on. And I'm also going to rerun my program from the beginning. And again, I like to do this whenever I change my settings around, just so I make sure my program is in a nice reset state. Okay, so I'm back at my prompt. So now let's go ahead and type in binls, just as I did before. And I notice nothing stops, no breakpoints, nothing. Okay, so I'll hit Control-C, get dropped back to the debugger, and now I'm going to set this special type of breakpoint that I want to show you. So previously we've looked at breakpoints, and we've also looked at watch points, both of which allow me to monitor state, and the first allows me to stop at predefined locations, and the second allows me to stop when certain variables or values or memory location contents change. This last type of breakpoint is known as a catch point, and catch points are unique in that they're triggered by special types of events, such as certain system calls. So for example, I can say catch fork to tell GDB to stop execution whenever a fork system call is detected. I can also do catch exec, for example. So let's see what happens now when I hit continue and type in binls as I've done before. So even though I don't have any breakpoints or watch points, notice that program execution is halted once it hits fork. So at this point, we're in the fork library function. I'm not interested in the implementation or stepping through this. So I'm going to go ahead and type finish to allow fork to complete. And that drops me back into, lo and behold, eval. And that's a little unclear, so let me type frame again to show you my current state. I also want to point out before looking at that, though, that my child process was forked, in fact, as a result of this line of code. And consequently, in the child process, it also went ahead and exec'd the binls program, and clearly it ran to completion because here's all of its output, interspersed with my debugging information. So remember the context. At this point, the child process has already completed. Okay, so I'm now looking at this line of code in the parent process, and I can hit next, and at this point the PID variable should have been populated, so I can look at that, and that's process 15073. Okay, and notice I'm about to go into add job. Add job's going to add the job that was just created in the parent process. So I'm going to step over that. And having executed add job, I should now be able to call foreground PID on jobs to tell me the PID of the foreground process, which is in fact 15073, which corresponds to the PID I received from the fork. I can also look at the first entry in the jobs array, yet another way of verifying the information about the foreground job, because I just added the job up here, line 186. Notice that it tells me, oh, I just added the job binls with job ID 1, state 1, meaning it's a foreground process, with PID 15073. So all looks well and good. Let me just go ahead and continue from here. Okay. So if you're a little confused now, that's a good thing, because this isn't expected. Notice what really should be happening is, well, my child process completed, it produced its output, and it exited. So what should be happening at this point is that my parent process should be reaping the child process, right? What happened then? Let's hit Control-C, find out where we are right now. So let me do a backtrace. And notice that in the shell, I'm currently sitting in waitFG, which called sleep, which is involved in doing something that we really don't understand and don't need to. Okay, so this is really kind of strange. And well, to debug this, we need to get back to a context we understand. So let me go ahead and type finish so that we finish up whatever nanosleep no cancel is. And now I'm back in sleep. And let me type finish to get back from sleep, and now I'm back in waitFG. And let's take a look at the code here. So the code for waitFG says, while FG PID jobs is equal to PID sleep for 1 second. Well, let's find out what FG PID is. It's 15073. Let's find out what PID is. It's 15073. We established this before we got to waitFG, in fact, back in eval. So what's going on? Well, here's what's happening. After the child process completed, notice that at that point we added the job and we jumped into waitFG. Okay, so this is a little confusing. Let's set a breakpoint now and see if we can really clear this up. So let's set a breakpoint at, where should we set a breakpoint? So we want to find out why the child didn't get reaped and why it didn't get removed from the jobs array, right? Because clearly it didn't get removed. Otherwise, foreground PID on jobs should report that 1503 is no longer the current foreground job. Okay, I hope you're following. So sigChild handler is the breakpoint we want to set. And let's go ahead and run this again. Okay, so binls again, and we're in fork again. Let's go ahead and type finish. And we are now in eval. I'm at line 180. Notice that my child process is now completed. Let's find out what happens next. So let me type N to step. Whoops. And let's see what just happened. So I type N to step through presumably to the next line of code within eval. But before I got there, a breakpoint got triggered. The sigChild handler got triggered. Why did that get triggered? Well, because the child process terminated. The child process terminated and it invoked the sigChild handler. So at this point, let me step once. If we take a look at the PID that we get back from wait null, we see that it's 15090. That is in fact the PID of the process we just reaped using wait. Now, if I examine the foreground PID currently, it tells me 0. Now think for a moment about what that means. That means that foreground PID, that function, and consequently my jobs array, doesn't know about this process that I just reaped. Now how could that be? Well, the reason for that is because addJob never got called yet. Remember, that takes place in eval. Let's take a look at the backtrace. If we look at eval, we got interrupted in eval. Let's select that frame by doing frame 2. So now looking at eval, I'm currently at line 180. Let me do a listing in eval. At line 180, I just did the fork and I have yet to do the addJob. Let me do another listing. Notice the addJob is at line 186. addJob has not yet run. Let me set a breakpoint at line 186 to see when that actually gets hit. Let me go back to the current frame. I'm in sigChild handler. And let's just keep going. So I'm going to go next again. and notice I called delete job. Now, of course, delete job really didn't do anything because the job itself wasn't at all inserted into the jobs array yet, and so that was kind of useless. Well, now let's just hit continue. Now that I've continued, notice I'm in eval again, where I set my breakpoint previously, getting ready to add the job that I just deleted. But of course I didn't delete it because I didn't add it yet. Again, hopefully this is making sense. Let's call fgpid on jobs again, just to see what that does, and it's still 0, which is nice because currently there is no foreground job. Remember, I just reaped it. But let's take one step with next. Now I've executed that line. Now if I do call fgpid jobs again, notice it says 15090. This is the job that terminated, was reaped, and now I'm inserting. Clearly this isn't a good thing. Let me continue, and we're now in that infinite loop in waitfg that we noticed earlier. This is a huge concurrency problem. And how do we deal with this? Well, that's where the screencast unfortunately ends. Dealing with this is an issue that you're going to have to figure out. Fortunately, the write-up has quite a few hints, and of course, this is something you'll probably want to ask questions about during lecture. Thanks.